there is a useful trick the night sky plays on the eye. It places stars on what looks like a single dark surface, as if the bright points above you all belong to one distant ceiling. A blue-white star near the horizon and a faint red one higher overhead can appear almost side by side. But the apparent pattern hides the true geometry. The stars are scattered through three-dimensional space, separated by gulfs so large that even light needs years to cross the nearest one. The closest star beyond the Sun is Proxima Centauri. Its light takes about 4¼ years to reach Earth. Sunlight reaches us in only a little more than 8 minutes, so the first neighboring star lies across a journey more than 250,000 times longer, even when measured at the speed of light. That single measurement changes the meaning of interstellar travel. A spacecraft does not merely need to escape Earth, pass the planets, and leave the Sun behind. It must cross a region whose scale is no longer measured conveniently in millions or billions of miles. The useful unit becomes the light year, a measure built from the fastest signal known to physics, and this is where warp drive enters the story. In 1994, physicist Miguel Alcubierre published a solution to Einstein's equations in which a region of space-time could be arranged so that space expands behind a spacecraft and contracts ahead of it. Within the mathematical construction, the ship itself does not locally outrun light in the ordinary sense. Instead, the geometry carrying it changes. Alcubierre also recognized a serious steel cost in his original model. The required space-time distortion involved exotic matter associated with negative energy density. The idea did not remain frozen in 1994. Later, researchers explored broader families of warp geometries, including sublight configurations intended to avoid some of the original model's most difficult energy requirements. Bobrick and Martyr described positive energy subliminal classes in 2021, and a 2024 paper presented a constant velocity subliminal construction designed to satisfy the classical energy conditions. But this is not the same thing as having a working engine. The interpretation of these newer constructions remains disputed. Recent technical criticism has challenged parts of the mathematical and physical reasoning behind several proposed physical warp drives, including the 2024 model. So the careful position is neither that warp travel has been solved, nor that every possible warp geometry has been ruled out. What exists today is a collection of mathematical ideas, unresolved physical questions, and no demonstrated spacecraft propulsion system. For our journey, that uncertainty matters, but there is another question that reaches beyond the engineering. Bayes. Suppose future physics is kinder than it looks today. Suppose researchers eventually discover a workable geometry. Suppose engineers learn how to create it, stabilize it, guide it, and supply whatever energy it requires. Suppose a ship can cross space at speeds that would make every spacecraft humanity has built. Would the galaxy finally become small? At first, the answer seems obvious. Move fast enough, and distant places become nearby places. Yet a galaxy is not simply a map waiting for a faster vehicle. It is a moving structure of stars separated by years of light travel, surrounded by gas, radiation, gravitational fields, and communication delays that belong to the geometry of the universe itself. Speed can shorten a crossing. It does not automatically erase the scale of the place being crossed. So we begin not with the imagined ship, but with the space around it. Because before asking how fast a warp drive could move, it helps to understand what the galaxy would still require it to overcome. To understand what a warp drive would actually change, it helps to remove the starship from the picture for a moment. Imagine instead a region of space with nothing inside it at all. Around that empty region, gravity is arranged in a very particular way. The geometry of space-time is different at the boundary than it is far away. In Miguel Alcubierre's original construction, The region ahead is described as contracting, while the region behind expands. The interior can remain locally ordinary, even while the larger geometry changes the way that interior moves relative to distant observers. This is the central idea behind the Alcubierre metric. The spacecraft does not accelerate through its local surroundings in the familiar way a rocket does. Instead, the spacetime containing the spacecraft is given a carefully constructed geometry. That distinction is the reason warp drive entered serious relativity at all. Special relativity prevents a massive object from being accelerated through ordinary local space until it reaches or passes the speed of light. The closer an ordinary spacecraft approaches that limit, the more energy continued acceleration requires. General relativity, however, describes something broader. It describes the geometry of spacetime itself. Spacetime is not required to remain rigid. It expands between distant galaxies as the universe evolves. It curves around stars. It bends light around galaxies and galaxy clusters. Near compact objects, it can become distorted enough that clocks at different locations no longer agree about how much time has passed. So Alcubierre's question was not whether a spacecraft could violate the local speed limit. It was whether space-time could be arranged so that the spacecraft never had to. The result was mathematically interesting and physically difficult. The original geometry required regions with negative energy density, something that appears in limited quantum contexts, but has never been demonstrated in the enormous, controllable form a macroscopic warp system would demand. Later work explored whether different geometries could reduce that problem, rather than accepting Alcubierre's first design as the only possible one. And that change in perspective matters. A warp drive is not one machine. It is a family of possible spacetime geometries. Some are faster than light in the mathematical description. Some remain below light speed. Some require energy conditions that ordinary matter does not satisfy. Others have been proposed specifically to remain within classical energy conditions. The name can make all of these ideas sound more similar than they are. In 2021, Alexei Bobrik and Gianni Martir developed a broader framework for thinking about them. Instead of treating the Alcubierre metric as the definition of warp travel, they described warp drives more generally as moving shells surrounding an interior region. Their work included subluminal configurations with positive energy and made another point that changes the popular picture considerably. A warp shell does not eliminate propulsion. It still has to move. That may sound like a small technical detail, but it removes one of the most common misunderstandings surrounding the idea. Warp drive is sometimes imagined as a way of telling the universe where you want to go and allowing curved space-time to do everything else. The mathematics does not grant that kind of freedom. A physical configuration has to be created. Its mass and energy have to come from somewhere. If the configuration changes velocity, something must produce that change. If it turns, the geometry must evolve appropriately. If it stops, the system must transition into another state. The bubble is not an exemption from dynamics, it becomes part of the dynamics. A 2024 study by Jared Fuchs and colleagues pushed the subluminal side of this research further. They presented a constant velocity warp configuration built from a positive mass-matter shell and reported that their numerical solution satisfied the classical energy conditions they tested. It was an important theoretical result precisely because it did not claim faster than light travel. That distinction is worth keeping close. Subluminal warp and superluminal warp are not two settings on the same engine. They may belong to very different physical categories. A below light speed geometry can remain causally connected in ways a faster than light configuration may not. It avoids some of the deepest problems associated with superluminal motion. but it also gives up the feature that made warp drive famous. The stars still require years, and there is another caution. A constant velocity mathematical solution is not the same thing as a spacecraft that can depart, that accelerate, steer around something, decelerate, and arrive. Recent work has continued examining exactly these gaps. Researchers have studied how proposed positive energy warp shells behave when acceleration and steering are introduced, and whether apparently favorable energy properties survive when the full physical boundary of a moving shell is treated more carefully. The subject is still developing rather than settling into a finished design. For a listener resting beneath an ordinary ceiling tonight, this may feel very distant from daily experience, yet the underlying idea is familiar in one small way. A boat crossing a river does not decide the shape of the river. It moves within a current that already exists. A warp concept asks whether, instead of building a faster boat, you could somehow engineer the current itself. General relativity allows us to describe what such currents of geometry would look like. It does not tell us that nature will let us build every geometry we can describe. That difference is one of the most important boundaries in theoretical physics. An equation can show that a spacetime is internally consistent under certain assumptions. It can reveal what energy distribution would be associated with that spacetime. It can expose horizons, instabilities, or other constraints. But the equation does not manufacture the matter. It does not build the power source. It does not tell you whether the configuration can be assembled from a normal initial state, and it does not guarantee that a system capable of existing at one constant velocity can be smoothly brought into existence, redirected, and brought to rest. This is where the modern warp drive story becomes more interesting than the familiar science fiction version. The question is no longer simply whether one famous equation allows a bubble. The deeper question is which space-time geometry nature permits as complete physical processes. A vehicle has to begin somewhere. It has to acquire motion. It has to respond to the universe outside its shell, and eventually, somewhere near another star, it has to stop. That last requirement will lead us away from the elegance of the metric itself and into the environment through which any real interstellar crossing would have to pass. Because between the Sun and Proxima Centauri, the space is thin, but it is not empty, and at very high speed, even almost nothing can become something you have to reckon with. Interstellar space carries a misleading name. It sounds like absence. Beyond the planets, beyond the distant reservoirs of icy bodies, beyond the region where the Sun's influence dominates the flow of charged particles, there appears to be almost nothing. No air, no oceans, no mountains, no weather in the familiar sense, only the long interval between one star and the next. But empty space is never entirely empty. Atoms of hydrogen drift through the galaxy. Some are neutral, some have been stripped into charged particles. Dust grains move through the same regions, built from heavier elements forged in earlier generations of stars. Magnetic fields thread through the gas. Cosmic rays cross these fields from distant sources, carrying energies that can make a single particle surprisingly destructive when it meets matter. At the speeds of ordinary spacecraft, this environment is thin enough to seem almost harmless. At a meaningful fraction of the speed of light, the same environment becomes a different problem. Consider a lone hydrogen atom. By itself, it is almost nothing. A proton, perhaps an electron, a piece of matter so small that trillions of them could pass through a large volume without ever becoming visible to the human eye. Now imagine a spacecraft moving toward that atom at 10% of the speed of light. From the spacecraft's frame of reference, the atom is approaching with the same relative speed. It is no longer a nearly motionless piece of interstellar gas. It is a projectile. Increase the speed of the spacecraft, and the collision energy rises quickly. At high relativistic velocities, individual atoms can strike with energies associated with forms of radiation, rather than the kind of mechanical impact we normally imagine when thinking about dust or gas. The danger comes not from one collision, but from continuity. A fast ship does not meet one atom. It sweeps through a corridor of interstellar material for years. Every square meter facing forward becomes a collection surface. Hydrogen arrives, helium arrives, occasional heavier nuclei arrive. Dust grains arrive much less often, but they carry far more mass than single atoms. Radiation arrives from directions that have nothing to do with the ship's motion. A real interstellar vehicle would have to survive all of it. This problem exists before warp drive enters the discussion. Relativistic spacecraft concepts have dealt with it for decades. Proposed solutions include physical shielding, magnetic fields, plasma structures, sacrificial layers, and combinations of these approaches. None is a simple answer. A thick shield increases mass. More mass makes acceleration harder. A magnetic shield can deflect charged particles, but neutral atoms do not respond to magnetic fields until they are ionized. Dust grains can carry charge, lose charge, fragment, or behave differently depending on their composition and velocity. And a shield that absorbs repeated high-energy impacts becomes a source of secondary radiation inside the vehicle. The obstacle is not that interstellar space is crowded. It is that speed changes what sparse material means. A light rain is harmless when you walk through it. The same water striking at an absurd velocity would no longer feel like rain. This is one of the strange consequences of trying to cross cosmic distances quickly. The faster the journey becomes, the more aggressively the environment presents itself. Warp geometry might change parts of this interaction, depending on the design. A spacecraft, enclosed inside a modified spacetime region, would not necessarily experience the surrounding medium in the same way as an ordinary vehicle moving directly through local space. The boundary of the warp region would become part of the problem. Gas and radiation would encounter the geometry before they encountered the crew. That may sound helpful. It may also create new complications. The behavior of matter near a moving warp boundary depends strongly on the particular metric being considered. Different geometries can redirect particles, concentrate them, spread them, or change the way an external observer describes their path. So there is no single universal answer to the question of what happens when a warp bubble meets interstellar gas. The answer depends on the bubble. This is another reason the phrase warp drive can conceal more than it explains. Two designs may share the name and behave very differently when they pass through the same cloud of hydrogen. For any future engineering program, the problem would become concrete very quickly. What happens to a neutral atom approaching the front boundary? Where does its energy go? Does it pass through the shell? Is it deflected around the vehicle? Does the field ionize it? Does radiation created by that interaction remain outside, or can some of it enter the interior region? What happens when a dust grain, far heavier than an atom, reaches the same boundary? These are not dramatic questions. They are the kinds of questions that determine whether a vehicle survives. A starship capable of crossing light years cannot rely on the hope that the route happens to be clean. The route itself must be characterized. That means interstellar navigation would involve more than pointing toward a star. Astronomers would need increasingly detailed maps of the material between departure and destination. Regions of enhanced gas density would matter. Nearby clouds would matter. Known structures in the local interstellar medium would matter. Even the timing of the journey could matter if changing stellar activity alters the radiation environment around the destination. This gives interstellar travel a character that is quite different from the open highway imagined in fiction. The space between stars is more like an ocean. whose water is almost infinitely thin. There are currents. There are regions with different densities. There are fields that extend across distances no ship has ever crossed. There are energetic particles arriving from events far beyond the route itself, and unlike an ocean, the faster you move through this medium, the harsher many of those interactions become. For a human crew, shielding would also have to solve another problem. Not all radiation comes from ahead. High-energy cosmic rays arrive from many directions. Some are atomic nuclei, moving near the speed of light. Their origins include powerful astrophysical environments such as supernova remnants and other energetic regions of the galaxy. Earth is protected from much of the space environment by an atmosphere and a planetary magnetic field. An interstellar ship would not have either unless it created its own equivalent. The vehicle would carry its habitat inside layers of engineered protection, perhaps surrounding living areas with water, structural materials, stored supplies, or other mass useful for absorbing radiation. But every protective kilogram must join the journey. That relationship follows interstellar engineering everywhere. More protection adds mass. More redundancy adds mass. More life support adds mass. More food adds mass. More equipment for repairing the equipment adds mass. A theoretical propulsion system may begin as a beautiful geometry on a page. A real starship becomes a moving ecosystem of compromises. This is true even if the crew feels no acceleration inside a warp region. They still need air. They still need thermal control. They still need power. They still produce waste heat. Their instruments still need to function. Their shielding still has to deal with whatever the exterior environment sends toward them. The geometry does not remove biology from the mission, and somewhere ahead, Proxima Centauri is not waiting in an empty chamber. It has its own stellar wind, its own magnetic activity, its own radiation environment. The destination is another physical system, not simply a coordinate. A ship crossing toward it would gradually leave one stellar environment and enter another. There may someday be elegant solutions to these problems. Perhaps a future warp shell could redirect incoming particles before they reach the craft. Perhaps advanced magnetic structures could turn part of the surrounding medium aside. Perhaps a vehicle could continually reshape its boundary to reduce damaging interactions. Those possibilities belong to future engineering, not to present capability. What matters now is the underlying lesson. Faster travel does not make the space between stars disappear. It changes the terms of the crossing. The emptiness acquires texture. A few atoms become radiation. A grain of dust becomes a serious event. A magnetic field becomes part of navigation, and a path that looks perfectly clear from Earth becomes a real environment stretching across more than 4 years of light. This is the first way the galaxy resists becoming small, not by placing a wall between the stars, by making even the emptiness matter once you try to cross it quickly. A journey between stars that becomes easy to overlook when the destination is drawn as a point on a map. The point is moving. Proxima Centauri is not fixed against a permanent background. Neither is the Sun. Both stars travel through the Milky Way, following their own paths, while the galaxy turns around its center. The nearby stars move with broadly similar galactic motion, but not perfectly together. Over years, decades, and centuries, their positions change. So an interstellar spacecraft cannot simply aim at where Proxima Centauri appears tonight. It has to aim at where Proxima Centauri will be when the spacecraft gets there. That difference is small enough to ignore when you are looking through a telescope. It becomes important when a vehicle is trying to place itself near another star after traveling several light years. The basic calculation is familiar. If you throw a ball towards someone who is walking, you do not throw toward the place where they are standing when the ball leaves your hand. You lead the target. You estimate where the person and the ball will meet. Interstellar navigation is the same idea, expanded until the distances become difficult to picture. Astronomers already measure stellar motion with remarkable precision. They track a star's position across the sky, its motion toward or away from us, and the way its apparent location shifts as Earth travels around the Sun. From these observations, a future mission could predict the destination star's trajectory. But prediction would only be the beginning. A spacecraft traveling for years would have to continually compare its expected path with its actual one. The reason is simple. No physical mission begins with perfect knowledge. A tiny error in velocity at departure can become a large positional error after crossing several light years. A slight misalignment that seems meaningless near the solar system can grow into a miss measured in millions of kilometers by the time the spacecraft reaches another star. For a fast interstellar probe, the navigation system would therefore need to work across scales that human transportation has never combined before. The vehicle might cross billions of kilometers while making corrections based on angles so small that they would be invisible without highly precise instruments. Stars themselves could serve as references. Pulsars might provide another possibility. These rapidly rotating stellar remnants produce pulses with patterns that can be measured very accurately, and researchers have long considered whether combinations of pulsar signals could someday help spacecraft determine their location far from Earth. An interstellar ship might also compare the apparent directions of many known stars, with an onboard catalogue gradually refining its position as the sky changes around it. The farther it travels, the more the familiar constellations would begin to distort. From Earth, the stars in a constellation appear to share a pattern because we see them projected onto the same sky. Move several light years away and that geometry changes. Some stars would shift more than others. A figure that seemed stable for thousands of years of human history would begin to reveal its true depth. The night sky would become a navigational instrument in a more literal sense than it has ever been for us. People have used stars to cross oceans for a very long time. A navigator at sea could watch where a familiar star rose above the horizon and use that repeated relationship to maintain direction. The stars seemed fixed because the voyage was short compared with the timescale of stellar motion. An interstellar crew would inherit the same basic instinct while entering a situation where the stars no longer provide an entirely fixed reference frame. They would still guide the traveler, but the traveler would be moving far enough for the map itself to change. A warp geometry would not remove this requirement. If the bubble remained below the speed of light, the crew might retain causal access to its boundary and, in principle, alter its trajectory as new measurements arrived. The details would depend on the physical design, but a controllable subluminal system could at least preserve something close to the ordinary relationship between navigation and correction. Observe, compare, correct, continue. The faster-than-light case becomes stranger. In Alcubierre-type superluminal geometries, the structure of space-time can create horizons around the moving region. Once the bubble exceeds light speed relative to distant space, parts of its boundary may no longer be reachable by signals sent from inside. This is not a matter of a weak transmitter. It comes from causal structure. Light defines how information can move locally through space-time. If part of the warp boundary lies beyond the region that signals from the ship can influence, then commands produced inside cannot simply travel forward and reshape that portion of the bubble whenever the crew wishes. The people inside might know that they need to change course. The geometry could prevent that information from reaching the place where the change has to occur. This is one of the deepest differences between a very fast spacecraft and a hypothetical superluminal warp system. A conventional spacecraft may be difficult to steer at relativistic speed, but its engines, computers, sensors, and structure remain connected through ordinary local cause and effect. A superluminal warp geometry can alter that relationship. The problem is built into the spacetime being used for transportation. If such a system were ever possible, mission planning might have to occur before the superluminal phase began. The trajectory could need to be prepared in advance, with the destination and stopping conditions already encoded into the geometry. That makes uncertainty more serious. A vehicle crossing ordinary space can respond to what it discovers. A vehicle whose forward boundary becomes causally inaccessible may have much less freedom. And the universe does not guarantee a perfectly predictable route. The stars move, planetary systems move with them. Objects orbit within those systems. The destination planet may be on the far side of its star when the ship arrives. A planet that looked promising when the mission departed may have been observed years in the past, because every image reaching Earth was already old when astronomers recorded it. This creates one of the quiet peculiarities of interstellar travel. You can never see the destination as it is now. When we observe Proxima Centauri tonight, we see light that left the system more than 4 years ago. If a spacecraft were dispatched immediately, the information used to plan the mission would already describe an earlier state of the system. During the crossing, new observations from Earth could improve the model, but those observations would also arrive with delay. The farther the ship moved from Earth, the more complicated the exchange would become. At some point, the spacecraft would become the best observatory available for its own destination. Its angle would be different. Its distance would be smaller. Its instruments could begin resolving details that were impossible to measure from the solar system. Navigation and discovery would merge. The ship would not merely follow a route, it would continuously improve the map it was following. There is something deeply familiar in that pattern. Early travelers on Earth often departed with maps that became less reliable near the edges of known territory. Coastlines had to be redrawn. Distances had to be corrected. Islands appeared where none had been recorded. The comparison only goes so far. Interstellar navigation is governed by very different scales and physics. But the underlying experience may be recognizable. You leave with a model. The journey teaches you where the model was incomplete. Then you steer using what you have learned. Near another star, the requirements become more demanding again. Arriving is not enough. The ship must match the destination system. A spacecraft approaching Proxima Centauri would enter a region dominated increasingly by that star's gravity and stellar environment. To remain there, rather than simply pass through at enormous speed, it would need to reduce its relative motion and settle into some useful trajectory. That might mean orbiting the star. It might mean approaching a planet. It might mean first entering a distant holding path while instruments examine the system in greater detail. Whatever the mission chooses, navigation changes from crossing an interstellar gulf to moving through a new planetary system. The scale compresses rapidly. Light years become astronomical units. Astronomical units become millions of kilometers. Eventually, if the goal is a planet or moon, the numbers shrink again. A mission that spent years crossing almost featureless interstellar distance would suddenly have to operate among worlds, orbital planes, radiation environments, and moving bodies. The final part of the journey could demand more precision than the entire crossing before it. This is why speed cannot be separated from control. A vehicle that moves quickly but cannot adjust accurately is not an interstellar transportation system. It is a projectile. The useful question is not simply how fast a warp bubble could travel. It is whether it could depart from one moving planetary system, cross a changing environment, follow another moving star, slow in the correct region, and arrive with enough control to do something meaningful once it gets there. Every one of those steps belongs to the journey, and none becomes smaller, merely because the maximum speed becomes larger. The galaxy keeps moving while you cross it. There is another distance hidden inside every interstellar journey. It is not measured in kilometers. It is measured in waiting. Imagine that a spacecraft has already solved the hardest mechanical parts of the crossing. Its engines are working. Its shielding is intact. Its navigation is accurate. Behind it, the sun has become another bright star. Ahead lies Proxima Centauri. Then someone aboard the ship sends a message home. Nothing dramatic has happened. Perhaps it is only a report from the day's observations, a few measurements, a photograph, a sentence meant for someone on Earth. The message leaves as electromagnetic radiation. And from that moment, the crew can do nothing to make it arrive sooner than light allows. That limit is not a weakness of radio. A laser would face the same constraint. So would any other communication system built from ordinary electromagnetic signals. As the ship moves farther from Earth, conversation stretches apart. A message sent from nearby space may need only minutes or hours to arrive. Farther out, the delay becomes days, eventually months. By the time the spacecraft is approaching another star, communication with Earth has become something closer to correspondence between different eras. Proxima Centauri lies about 4¼ light years away. Even a signal traveling at light speed between Earth and the Proxima system therefore needs about 4¼ years in one direction. A question sent from one system and answered immediately from the other would require roughly 8½ years for the complete exchange. NASA studies of possible missions to Proxima have treated this long round-trip delay as a reason that any such spacecraft would require a high degree of autonomy. That fact survives almost every improvement in propulsion. Build a better rocket, and it remains. Build a fusion engine, and it remains. Build a powerful laser sail, and it remains. If a future warp system travels below light speed and communicates using ordinary light, the delay remains. The spacecraft may reach its destination sooner than earlier vehicles could have imagined, but Earth cannot reach across several light years and conduct a conversation in real time. This is a different kind of isolation from physical distance. A crew might still receive messages from home. They might hear familiar voices. They might watch recordings made by people they love. But each message belongs to an earlier Earth. A reply belongs to a later one. The farther apart the two worlds become, the more every exchange begins to resemble a dialogue written across time, rather than a conversation happening in a shared present. There is no moment when the crew looks through a screen and sees Earth as it is. There is only Earth as it was when the signal left. The same is true in reverse. If the ship sends a photograph from 2 light years away, Earth receives an image of the crew from 2 years earlier. If a mechanical problem appears aboard the spacecraft, engineers on Earth cannot examine it immediately. By the time the first description arrives, the crew may already have solved it, or the system may already have failed. Instructions sent back from Earth would begin another journey across the same distance. This means an interstellar spacecraft would gradually become its own technical world. It could carry large stores of knowledge. It could carry software capable of assisting with diagnosis. Its crew might include people trained across overlapping specialties, so that a medical problem, an electrical failure, a life support malfunction, or a navigation error does not depend on expertise waiting several light years away. Automation could become more capable than anything available today. Machines might monitor other machines continuously. Replacement parts could be manufactured aboard the ship. Some failures might be corrected before a human crew member even knows they occurred. Yet autonomy changes the mission in a way speed alone cannot undo. The farther the spacecraft travels, the less meaningful it becomes to say that Earth is controlling it. Earth may have designed the mission. Earth may have launched it. Earth may continue sending advice. But the people and machines aboard would increasingly make decisions locally because the universe has made consultation too slow. That would be true even if the trip itself became remarkably fast by present standards. A crossing would still contain long periods in which any useful response from home arrives after the decision has already been made, and time has another role in the story. For an ordinary spacecraft traveling through space at a large fraction of the speed of light, special relativity changes the relationship between time aboard the spacecraft and time measured by observers who remain behind. A moving clock is measured to run more slowly than an otherwise identical clock at rest in the observer's frame. This is not a mechanical defect in the clock. All processes traveling with it share the same proper time. The effect follows from the geometry of special relativity and has been confirmed through many forms of experiment. At modest speeds, the difference is tiny. At speeds approaching that of light, it becomes important. Suppose a conventional spacecraft could somehow maintain a cruise velocity of 90% of light speed. Earth would measure the journey to Proxima Centauri as taking a little under 5 years if acceleration and braking were ignored for the moment. The people aboard would experience less elapsed time than observers who remained with Earth. Push the velocity closer to light speed, and the difference grows. From the traveler's point of view, enough relativistic speed could make enormous journeys fit inside a human lifetime. That sounds at first as if relativity itself offers a way to make the galaxy smaller, but only for the traveler. The stars do not move closer together in Earth's frame because a spacecraft carries a fast clock. A civilization remaining on Earth still waits for the ship to cross the distance. If travelers continued deep into the galaxy at extreme relativistic speed, they could experience much less time than the centuries or millennia measured by the world that launched them. They might reach places that would otherwise seem unreachable within one lifetime. But returning home could mean returning to a civilization that had aged far beyond them. This is sometimes called the twin effect, although the name can make it sound more mysterious than it is. Two people follow different paths through space-time. When they meet again, their clocks can show different amounts of elapsed proper time. The difference is physical. Bodies aged according to the time along their own paths. Memories form according to it. Heartbeats happen according to it. The traveler does not feel time slowing. A minute aboard the spacecraft feels like a minute. Sleep still lasts for hours. A meal still cools. A conversation still unfolds at its ordinary pace. Only when clocks following different paths are compared does the accumulated difference become clear. This creates an unusual choice for conventional interstellar travel. Go slowly, and the voyage consumes more of the crew's life. Go close enough to light speed, and the crew may experience a shorter crossing, but they become increasingly separated from the timeline of the civilization they left. Either way, distance has taken something. Warp drive ideas were partly attractive because they appeared to offer a different relationship with this problem. In an Alcubierre style construction, the spacecraft can remain locally at rest inside its interior region, while the surrounding space-time geometry supplies the larger motion. In the original idealized description, the occupants need not experience the ordinary local acceleration associated with pushing a vehicle to enormous speed. But it is important not to carry that observation too far. There is no working warp spacecraft whose clocks can be tested. Different proposed metrics have different geometries. Statements about how much proper time would pass aboard a real vehicle depend on the actual spacetime that could be constructed, how the bubble is created, how it accelerates, and how it returns to ordinary conditions. The mathematics does not yet justify treating every imagined warp journey as a place where all problems of time simply disappear. And there is a deeper difficulty. If faster than light travel is introduced, the light speed boundary in relativity is not merely a limit placed on engines. It helps define which events can influence other events. Light cones describe the causal structure surrounding every event in space-time. Within those cones lie places that ordinary signals can reach. Outside them lie events that cannot be connected by slower than light communication from that starting point. If information could be carried outside those ordinary causal relationships in the wrong way, different observers could disagree, not merely about how long a journey took, but about the order in which separated events occurred. That possibility is why faster than light motion is tied so closely to discussions of causality. It is also why making a superluminal warp geometry mathematically writable does not automatically make it physically acceptable. A transportation system has to do more than deliver a ship. It has to exist within a universe where cause still leads consistently to effect. For now, the less speculative lesson is already enough. At sublight speed, the communication boundary is clear. The farther the travelers go, the longer every message takes. This could shape an interstellar civilization more profoundly than the propulsion system itself. Imagine a settlement established near another star. Perhaps it begins with a few researchers, then a larger habitat. Then children are born there who have never seen the solar system except through delayed images. Earth can send discoveries, art, history, technical knowledge, and personal messages. The settlement can send its own work back. But each side receives the other in layers from the past. There could be no single conversation joining both societies. A political decision made on Earth might not be known at Proxima for more than 4 years. A response made at Proxima would need more than 4 additional years to return. By the time Earth received it, the original question could belong to an administration, institution, or generation that had already changed. The distance would encourage local decision-making, not because people wanted separation, but because practical life would demand it. Interstellar civilization, if it ever develops under known communication physics, may therefore look less like one enormous connected society and more like a collection of neighboring cultures, exchanging delayed letters of light. Each system could know that the others exist. Each could learn from them. Each could care about them. Yet each would live mostly in its own present. For thousands of years, human beings looking upward could imagine that the stars shared one sky, because the light from all of them arrived together at the eye. Travel reveals something different. Every star carries its own clock of distance. Every signal crossing that distance carries a piece of the past. And even if a future ship learns to move between the stars, the people on either side may still have to learn how to live without sharing the same now. Once a warp drive is drawn as a geometry rather than a starship, an uncomfortable question becomes impossible to avoid. What builds the geometry? Einstein's equations do not allow space-time curvature to appear without a physical source. Matter, g-pressure, momentum, stresses are connected to the shape of space-time. If a proposed warp region requires a particular curvature, then somewhere in the description there must be something capable of producing the corresponding gravitational field. This is where the elegant picture of contracted space ahead and expanded space behind becomes a problem of physical inventory. You have to ask what is in the shell, how much of it is required, how it is arranged, how that arrangement is maintained, and eventually how it is changed. Miguel Alcubierre's original metric, made this difficulty obvious because portions of its required energy density were negative. That placed the proposal outside anything engineers know how to assemble on macroscopic scales. Later work changed the question. Instead of asking whether Alcubierre's particular geometry could somehow be manufactured, researchers began searching the much larger space of possible warp geometry. In 2020, Alexei Bobrik and Gianni Martiri described positive energy subliminal warp configurations and emphasized that a physical warp drive should be thought of as a moving material system, not as a magical bubble detached from ordinary dynamics. Their analysis also pointed toward a limitation that is easy to miss. A warp configuration does not automatically accelerate itself. That means the phrase warp propulsion can be misleading. A geometry can describe a region already moving at some velocity without explaining the complete history that brought it to that velocity. A drawing of a train moving across a page does not tell you what started the train. For an interstellar vehicle, departure matters just as much as cruise. The system begins somewhere near a planet or an orbital facility. It must enter its traveling state without destroying its surroundings. It must gain velocity. It must possibly change direction. Then, after crossing years of interstellar space, it has to slow again. A physically useful warp drive must therefore be more than a constant velocity solution. It needs a beginning and an end. The 2024 constant velocity solution developed by Jared Fuchs and colleagues was important within this narrower context. Their model combined a matter shell with a shift vector distribution and produced a subliminal spacetime that, in their numerical analysis, satisfied the classical energy conditions. It showed that at least some warp-like geometries can be written without the negative energy requirement associated with the original Alcubierre construction. But the words constant velocity carry much of the story. The model does not by itself give humanity a launch procedure. It does not provide a finished engine. It does not tell a ship how to leave Earth, turn toward another star, correct its path, and settle into orbit when it arrives. Those questions lead directly to conservation laws. If a massive system changes its motion, momentum has to go somewhere. A rocket handles this by throwing material backward. A photon rocket can do it by sending radiation in the opposite direction. A sail can exchange momentum with light. A spacecraft near a planet can borrow a little momentum through a gravitational encounter. The mechanisms differ, but the accounting remains. Motion does not change simply because the passengers are surrounded by unusual geometry. A recent 2026 preprint has explored this issue explicitly for positive energy warp-like systems. In that construction, steering is achieved through radiation and corresponding mass energy loss, rather than through a self-propelled distortion that changes direction for free. The result is still theoretical and does not settle the wider field, but it illustrates an important principle. Once acceleration and steering are included, the energy and momentum budget returns to the center of the problem. That may turn out to be one of the recurring themes of warp research. Every time geometry appears to remove one familiar difficulty, another form of physical bookkeeping appears beneath it. Perhaps the crew need not feel enormous acceleration, then the shell still has to change momentum. Perhaps negative energy can be avoided in a subliminal design. Then the required positive energy configuration still has to be assembled. Perhaps the interior can remain flat. Then the boundary between that interior and the external universe becomes the place where the difficult physics is concentrated. None of this makes the research meaningless. It makes it more physical. A useful theory gradually has to become less like a shape drawn in space-time and more like an object with a history. It must be constructed from some earlier state. It must survive. It must respond. and it must eventually be dismantled or transformed into something else. That requirement introduces engineering problems for which no detailed specifications yet exist. A future warp system would need some way to control the distribution of matter and energy responsible for its geometry. The distribution could not merely be approximately correct. The spacetime produced by it would have to remain within whatever tolerances keep the interior safe and the trajectory predictable. If the configuration drifted, the geometry would drift with it. If part of the system failed, the consequence might not resemble an ordinary engine shutting down. We do not yet know what failure would mean, because no physical warp shell has ever been constructed. There is no experimental history, no damaged prototype, no engineering handbook filled with lessons learned from earlier vehicles. There is only theory gradually becoming more detailed. This is an important place to separate imagination from prediction. It is easy to invent materials with convenient names and assign them whatever properties a starship needs. Science cannot do that. Until the source of a geometry is understood in experimentally accessible physics, the honest description is that the required technology has not been established. The same caution applies to power. There is no single number called the energy requirement of warp drive. Different metrics describe different structures, different bubble sizes, velocities, matter distributions, and boundary conditions produce different energy accounting. So, statements that warp drive requires one fixed planetary mass, one fixed reactor output, or one fixed quantity of fuel can become misleading when transferred from one theoretical model to another. The field itself has changed partly because researchers learned that geometry matters enormously. Change the geometry and the required stress energy changes. But reduction is not elimination. Even a positive energy solution must still contain energy. A civilization able to manipulate spacetime deliberately would first need to understand how to concentrate, configure, measure, and control that energy with a precision far beyond anything demonstrated today. And this is where the timescale of the problem begins to change. The first warp drive paper appeared only a few decades ago. That is, a very short interval in the development of physics. Human beings have often lived through long spaces between understanding a principle and learning how to turn that principle into dependable machinery. The people who first studied electricity did not live inside a world of global power grids. The early investigators of electromagnetism did not watch spacecraft communicate across the solar system. The foundations of rocketry were developed long before humans stood on the moon. A scientific idea can belong to one generation, while its mature engineering belongs to another. Warp physics, if it ever leads to transportation, may demand this kind of patience on a much larger scale. You can imagine researchers who never see a vehicle carrying forward a calculation that later becomes indispensable. Then another generation measures an effect the first could only estimate. Another develops the materials. Another learns how to control the system. Eventually, people whose names are not yet known may work on problems whose vocabulary does not yet exist. There is no promise in that image. Many scientific ideas never become machines. Some fail because nature refuses the final step. Others become useful in ways their originators never anticipated. But if a warp system is physically possible, its path from equation to vehicle would almost certainly be built from accumulated work rather than one sudden invention. And even at the end of that path, the machine would not escape conservation laws. It would carry mass. It would contain energy. It would exchange momentum with something. It would create heat. It would need control. It would have finite tolerances. It would exist inside the same universe it was designed to cross. That may sound less spectacular than a starship disappearing in a flash of distorted light. it is also more interesting, because the deeper challenge of interstellar travel is not finding one loophole and escaping physics. It is learning to work with many layers of physics at once. Relativity determines the geometry. Matter provides the source. Conservation laws govern motion. Thermodynamics follows the machinery. Radiation follows the energy. Engineering has to keep all of them compatible long enough for the ship to reach another stop. And even if some future civilization manages all of that, another boundary will still be waiting. A warp drive may change how the ship moves through the galaxy. It cannot decide what kind of galaxy is waiting when the ship arrives. Reaching another star would not end the uncertainty. It would only change its shape. For generations, interstellar travel has often been imagined as a problem with a clear destination on the other side. Build the ship, cross the distance, arrive at the new world. But astronomy rarely gives us destinations that are known in that way. It gives us measurements, mass limits, orbital periods, spectra, brightness changes, upper and lower limits, hints of atmospheres, occasional clues about temperature, chemistry, or magnetic activity. Then, between those measurements, there are large regions of uncertainty. Proxima Centauri offers a useful example because it is so close. We know the star is a red dwarf, smaller and cooler than the Sun. We know it is magnetically active. We know it produces flares capable of releasing energetic radiation into the surrounding planetary environment. We also know that at least one planet, Proxima Centauri b, moves through the region around the star where temperatures could, under some atmospheric conditions, permit liquid water. That phrase carries more caution than it sometimes seems to. The habitable zone does not mean a planet is habitable. It is mainly a statement about distance from a star and the amount of energy a planet receives. Whether liquid water can actually remain on the surface depends on much more. An atmosphere matters, its composition matters, its thickness matters, clouds matter, the planet's rotation matters, geological cycling may matter, stellar radiation matters, a magnetic field may matter. And for a planet orbiting an active red dwarf, the history of the star can be as important as its present brightness. A young red dwarf can spend a long time in an energetic phase. If a nearby planet formed with an atmosphere, repeated ultraviolet and X-ray exposure could alter that atmosphere over time. Some gases might be stripped away. Others might be regenerated through volcanism or surface chemistry. A magnetic field could change the interaction. A thick atmosphere might provide protection. Or the planet may have evolved along a path very different from anything represented in the solar system. From Earth, we cannot yet reconstruct that full history with confidence. So a crew arriving at Proxima Centauri would not be arriving at a world already understood. They would be arriving at the beginning of much better observation. At first, the star itself would dominate the scene. Then the planets would become objects with real geography rather than inferred properties. Their atmospheres, if they have them, could be studied from nearby space. Weather patterns might become visible. Surface contrasts might appear. Auroras could reveal magnetic interactions. Moons, rings, dust, or small bodies that were invisible from Earth might emerge from the background. The system would stop being a handful of data points and become a place. And that change could contain surprises in either direction. A planet described from Earth as promising might prove hostile. A world dismissed as uninteresting might contain the most valuable scientific environment in the system. A moon we did not know existed might become the destination that matters most. This is one reason interstellar missions cannot be planned, like ordinary journeys between known cities. The target itself is incomplete. The closer you get, the more the mission may have to change. Long before human beings crossed oceans with accurate charts, coastlines were often represented by fragments of knowledge carried from earlier voyages. A harbor might be placed correctly, while the land beyond it remained poorly understood. A chain of islands could be known without anyone having mapped every passage between them. The next traveler did not simply follow the map. The next traveler helped make it. An interstellar mission would inherit a far more advanced scientific tradition, but it would still encounter a version of the same boundary. Our maps of nearby planetary systems are already remarkable. They are also maps made from light. A spacecraft inside those systems would begin replacing inference with proximity. That may be the true scientific value of the first interstellar crossings. Not settlement, not expansion, not the immediate discovery of another Earth. Simply the opportunity to study a second planetary system from within. The solar system has taught us how misleading distance can be. Before spacecraft visited the outer planets, even the best telescopes left major questions unresolved. Voyager transformed the giant planets from remote objects into complicated systems of rings, magnetospheres, atmospheres, moons, storms, volcanoes, and fractured ice. Later missions did the same in finer detail. Each improvement in proximity changed not only what we knew, but what questions became possible. The first successful mission to another star could produce the same kind of shift on a larger scale, and that possibility changes the meaning of warp drive again. If future warp technology remains subliminal, then the nearest stars become difficult expeditions rather than casual destinations. That may still be enough. A civilization does not need the entire galaxy to become accessible before interstellar travel becomes scientifically valuable. 1. Neighboring system could occupy researchers for centuries. Alpha Centauri alone contains 3 stars with very different properties. The nearby red dwarf systems offer another laboratory. More distant sun-like stars offer another. Each successful crossing would add a planetary system to the small number humanity can study directly. That is a slower future than the one usually imagined. It may also be richer. The galaxy contains so many stars that the word exploration begins to lose its ordinary meaning. Even if a civilization could reach one new system every year, the Milky Way would still contain far more stars than any individual lifetime could encounter. Increase the pace dramatically and the numbers remain enormous. 100 billion stars cannot be turned into familiar places by speed alone. The scale defeats familiarity long before it defeats engineering. This leads naturally to another question. If interstellar travel is possible at all, why does the sky not already show clear evidence that someone else has done it? The question is often associated with the Fermi paradox, although the modern discussion contains many versions of the problem. The basic tension is simple. The Milky Way is old. Many stars are older than the Sun. Planets are common. If technological life has appeared elsewhere, then some civilizations may have had enormous spans of time in which to develop. Even without faster than light travel, a civilization spreading gradually from one system to neighboring systems could, under some assumptions, move through large parts of the galaxy on timescales much shorter than the age of the Milky Way. And yet, we do not have confirmed evidence of such a civilization. That absence does not tell us why. It does not prove that interstellar travel is impossible. It does not prove that intelligent life is rare. It does not prove that advanced civilizations choose isolation. There are too many unknowns. The origin of life may be uncommon. Complex life may be uncommon. Technological intelligence may be short-lived. Civilizations may not expand. Their technology may become difficult for us to recognize. Their signals may be weak, brief, directional, or separated from us by long intervals. We may simply have searched too small a portion of the possible sky, frequencies, technologies, and timescales. Distance is only one possible part of the answer. But it is a part worth noticing. because it does not depend on biology or culture. Every civilization in the Milky Way, if others exist, begins inside the same general physical framework. Their stars may differ, their planets may differ, their bodies, senses, and histories could be unlike anything we can imagine. But the distance between stellar systems remains measured in light years. Radiation still moves through space-time at finite speed. Energy still has to be accounted for. A vehicle still has to survive the environment it crosses. Information still arrives late. Whatever intelligence appears elsewhere does not receive a smaller galaxy. This creates a possibility that is less dramatic than many solutions to the Fermi paradox. Perhaps advanced civilizations do cross between stars. Perhaps they simply do it rarely. A research expedition every few decades would not fill the galaxy with obvious traffic. A civilization that builds permanent settlements only around a handful of neighboring stars could remain almost invisible from here. A culture might spend millions of years developing within one planetary system because there is no urgent physical reason to expand farther. Another might send machines rather than people. Another might explore through telescopes so powerful that travel provides too little benefit for the cost. And some may try to cross the distance and fail. The silence of the sky leaves all of these possibilities open. For now, we have only one technological civilization available for direct study, ours. And our own history suggests that exploration does not require a destination to become easy before it becomes meaningful. Human beings crossed dangerous oceans long before those crossings became routine. We sent spacecraft toward planets years before we knew exactly what the cameras would find. Voyager left Earth without any possibility of repair once it reached the outer solar system. Every one of those journeys was limited by the technology of its time. None required the entire world beyond the horizon to become small. Interstellar travel may follow the same pattern. The first successful mission might not announce the beginning of a galaxy-wide civilization. It might simply become the first thread between two stellar systems. A fragile connection, a stream of delayed data, a few human lives, or perhaps only machines, learning what exists around another sun. Then another mission may follow decades later, and another after that. The galaxy would remain enormous, the distances would remain inconvenient, but the map would begin to acquire places. Humanity had actually visited. There is a present-night version of that thought. Somewhere beyond the walls around you, the nearest stars are following their paths through the galaxy, whether anyone travels to them or not. Their planets continue orbiting, their atmospheres change, their rocks weather, their stars flare, rotate, and age. Nothing there depends on our arrival. The value of crossing the distance would come from what we learn when two previously isolated regions of knowledge finally meet. Warp drive, if it ever becomes physical technology, may not turn the Milky Way into a neighborhood. It may do something quieter. It may allow the first few doors between distant houses to open. A warp drive that failed to make the galaxy small could still change the meaning of home. The solar system is already a place of enormous distances. Earth and the Moon are close enough that light crosses the gap in a little more than a second. Sunlight takes a little more than 8 minutes to reach Earth. By the time you move outward to the orbit of Neptune, light itself needs a little over 4 hours to cover the distance from the Sun. For machines built by humans, those same distances become years. A probe bound for the outer planets must be launched onto a carefully chosen trajectory, often using planetary gravity to reshape its path. A mission may spend much of a decade simply traveling before its main scientific work begins. Once it arrives, every command from Earth still crosses space at light speed, and every reply makes the same journey back. This has shaped the way we explore. We build spacecraft that can survive long intervals with limited intervention. We plan observations years before the data exist. We design instruments knowing that if a component fails beyond repair, no technician can travel out to replace it. That is the normal rhythm of planetary science today. A future propulsion system capable of maintaining even a substantial fraction of light speed would change that rhythm before it ever carried anyone to another star. Mars would no longer feel like a destination separated from Earth by seasons of travel. The giant planets would no longer require journeys measured in years. The Kuiper Belt would remain physically immense, but access to it would take on a scale more familiar to human planning. The transformation would not depend on exceeding light speed. Any technology capable of moving large spacecraft through the solar system at speeds far beyond those of present propulsion would reorganize what exploration means. That possibility is easy to overlook because warp drive is almost always discussed beside stars. But the first place such a technology would matter is much closer. It would matter around the worlds already bound to the sun. The solar system contains environments more varied than a simple diagram of 8 planets suggests. There are airless surfaces, thick atmospheres, subsurface oceans, rings, volcanic moons, metallic asteroids, carbon-rich bodies, frozen objects, and regions where sunlight has weakened to a pale fraction of what reaches Earth. We have visited many of these places only briefly. Some have been seen during a single flyby. Some have been orbited for years by robotic spacecraft. Many small bodies remain little more than points of light, with estimated sizes, colors, and orbits. Faster transportation would not make those worlds easier to understand automatically, but it would change how often we could return. That difference matters. Science becomes deeper when observation can be repeated. A storm can be followed through seasons. A plume can be revisited after it changes. A lander can be replaced when its instruments fail. A sample can be collected, returned, examined, and followed by a second mission around what the first sample revealed. Instead of treating each outer system expedition as a rare event, separated by long cruise phases, a future civilization could begin treating distant worlds as continuing research sites. The shift would resemble the difference between seeing a coastline once from a passing ship and maintaining an observatory there. There is also a practical reason this nearer frontier matters to the warp drive question. Interstellar travel combines almost every difficult problem at once: long isolation, radiation, closed life support, autonomous medicine, repair without rescue, navigation across light years, delayed communication, arrival in a system that is only partly understood. The solar system offers a place to learn many of those lessons without adding the full distance between stars. A vehicle capable of fast travel to the outer planets could test long-duration habitats while remaining within the sun's domain. Engineers could learn how propulsion behaves far from Earth. Navigation systems could mature across billions of kilometers. Closed ecosystems could be tested during missions that are demanding but still connected to one planetary system. Before an interstellar ship becomes a bridge between suns, the technology behind it may first become a bridge between worlds that already share one sun. That progression would have a human side as well. For most of history, the planets were lights in the sky. People watched them wander against the stars without knowing what their surfaces looked like. Then telescopes gave them disks. Later instruments revealed bands, caps, rings, clouds, and moons. Spacecraft turned some of those distant lights into landscapes. Spacecraft then turned remote objects into mapped places with weather, geology, rings, atmospheres, and landscapes no telescope on Earth had shown in comparable detail. Each generation inherited a solar system that felt somewhat less abstract than the one before it. A major advance in propulsion would continue that same movement. not by reducing the physical distances, by reducing the amount of human life consumed in crossing them. That is an important distinction. Distance and accessibility are not the same thing. A mountain does not become shorter because a railway reaches its base. An ocean does not become narrower because aircraft cross it in hours. The geography remains. What changes is how often people can move through it and how much of a lifetime the crossing requires. The same could happen here. Neptune would remain billions of kilometers from Earth. The Kuiper Belt would remain a broad region extending far beyond the major planets. Signals would still obey the speed of light, but the solar system could become operationally closer while remaining physically unchanged. That may be the most realistic way to think about what advanced propulsion does. It changes relationships before it changes boundaries. Today, the outer solar system is a place we send machines toward and then wait. In another technological era, it could become a place where observatories are maintained. Samples move routinely between laboratories, and researchers spend part of their working far from Earth before returning. None of that requires the Milky Way to become manageable. It only requires our own system to become traversable, human schedules, and that reframes the apparent failure of subliminal warp. If faster than light travel proves impossible, a physical warp technology would not become useless. It might still be one of the most consequential transportation advances a spacefaring civilization could develop. A propulsion system does not have to reach another star in days to transform civilization. It only has to change what can be reached reliably within the time. People are willing and able to travel. There is a kind of proportion in this. The nearest star is more than 4 light years away. But before that crossing begins, there is an entire planetary system around us. A system whose worlds formed from the same broad disk of material. A system whose objects have been trading gravity, impacts, ice, dust, and radiation for billions of years. A system that still contains unanswered questions close enough for our instruments to reach. The desire to cross to another sun does not become smaller when we recognize this. It becomes better placed. You can imagine a future in which interstellar missions are rare, prepared across decades, and treated as commitments spanning generations. At the same time, travel within the solar system might become ordinary enough that laboratories, habitats, and observatories exist at many distances from the sun. The two futures are not in conflict. One is the difficult extension of the other. First, a civilization learns to move confidently through the system that formed it. Then, perhaps, it attempts the gap beyond. And if that day comes, the first interstellar crew would leave from a solar system that no longer feels like a collection of remote dots. They would leave from a place already explored in depth. A place with histories on many worlds. A place with roots, instruments, settlements, and generations of people accustomed to living far from Earth. The starship would not depart from one planet, trying suddenly to cross the galaxy. It would depart from a mature planetary civilization, taking one further step. That may be the scale warp drive is best suited to reveal. Not a Milky Way made small, a home system made large enough to inhabit fully and beyond its outer reaches. The nearest stars would still keep their measured distance. The great temptation in thinking about warp drive is to imagine that distance is only a technical inconvenience. Build a better machine, and perhaps the inconvenience disappears. But the deeper lesson is almost the opposite. Technology can change how we experience distance without changing what distance is. 4 light years remain 4 light years, whether the crossing takes 70,000 years, 40 years, 5 years, or some shorter interval allowed by a future theory we do not yet possess. The separation between the Sun and its neighboring stars is written into the arrangement of matter across the galaxy. Propulsion changes the traveler. It does not rearrange the Milky Way into a smaller place. That distinction may matter more than any particular warp metric. For most of human history, the night sky was unreachable in a very literal sense. The moon could be watched, but not visited. Mars could be tracked, but not photographed from orbit. The outer planets were points of light whose true complexity remained hidden. Then, over a few generations, machines crossed those distances. The moon did not move closer. Mars did not move closer. Jupiter did not move closer. We simply learned how to spend less of our lives reaching them. Perhaps interstellar travel will someday follow the same pattern, although on a scale far beyond anything humanity has attempted so far. The first successful journey to another star, if it ever happens, may not resemble the effortless movement of fiction. It may be a carefully prepared expedition supported by generations of research, enormous infrastructure, and a vehicle designed to survive years away from any possibility of rescue. The people who build it may understand the limits of the journey better than anyone who dreamed about it before them. They may know exactly how much radiation shielding is required. They may know how the surrounding interstellar medium interacts with the vehicle. They may know how to navigate toward a moving star and how to enter its planetary system without arriving as an uncontrolled projectile. They may carry medical systems, manufacturing capability, autonomous software, and enough technical knowledge to solve problems with no immediate help from Earth. And even then, the first thing waiting outside the solar system will not be convenience. It will be separation. Messages will take years. Earth will become an object remembered through delayed light. The destination will reveal details that no telescope at home could fully predict. The travelers will discover a planetary system that has spent billions of years developing without them. That may be what crossing between stars really means, not defeating distance, entering into it. There is a subtle change of perspective hidden there. Science fiction often makes the galaxy familiar by shortening travel. One star becomes a port, another becomes a colony, another becomes somewhere you can leave in the morning and reach before the story has grown old. Real astronomy does something else. It preserves the distances. It tells you that the light reaching your eyes has been traveling for years before you noticed it. It tells you that every visible star occupies its own region of space, with planets and histories unfolding beyond immediate contact with ours. It tells you that the galaxy is not one place in the human sense. It is a collection of places separated by time. Perhaps future technology will connect some of them. Perhaps only the nearest. Perhaps machines will travel first, sending observations back across the same distances they crossed. Perhaps human crews will follow much later. Perhaps faster than light travel will remain an elegant mathematical question rather than a physical technology. We do not know. There is no need to turn that uncertainty into either optimism or disappointment. The unanswered part is part of the science. Warp research has already forced physicists to ask useful questions about the relationship between geometry, energy, motion, and causality. Even if no practical starship ever emerges from the work, those questions still sharpen our understanding of what general relativity permits and where its limits may lie. And if some form of warp technology does become physical, its first great achievement may not be the conquest of interstellar space. It may be more local. The solar system could become easier to cross. The outer planets could become accessible on timescales that allow repeated human exploration. Distant moons, dwarf planets, and icy regions could become places that are revisited rather than glimpsed once by a passing spacecraft. Our civilization could learn what it means to inhabit one planetary system before asking what it means to connect to. There is a kind of maturity in that sequence. The desire to reach the stars remains. But the stars do not have to become nearby for the desire to matter. Their distance is part of what makes the question interesting. A neighboring star is close enough for its light to reach us within a few years, yet far enough that no human being has ever crossed even a meaningful fraction of the gap. That contrast tells us where we are. We live inside one gravitational household, orbiting one ordinary star, surrounded by worlds we have only begun to understand. Beyond them are other stars, beyond those more. The Milky Way continues for tens of thousands of light years in every direction along its disk, containing regions that even light requires enormous spans of time to cross. No finite speed turns that into a small place. That may be the point worth carrying away from the idea of warp drive. The universe does not need to become convenient before it becomes reachable. And reachability does not need to become routine before it becomes meaningful. Someday, a spacecraft may leave the sun behind and continue outward until the planets are no longer the brightest landmarks around it. The familiar constellations will slowly change. The sun will become one star among many. Ahead, another system will grow brighter. Its worlds will move through orbits that no human eye has seen from nearby, and somewhere between the two stars, the travelers will be surrounded by distance that generations before them could. Nothing about that distance will have vanished, but for the first time, someone may be crossing it. The stars can remain far away and still be reached.